Welcome back, everyone. Let's continue coding out our walkthrough for the adaptive boost algorithm. In part 2, we're now focusing on the model. I'm going to head back to the notebook where we left off last time. Alright, here I am back in the notebook where we left off last time. We did a train test split. Let's go ahead and create a model. We will say from scikit-learn.ensemble import and begin to type ADA, and you should be able to see the ADA boost classifier. Keep in mind you can also perform regression with ADA boost. So we import ADA boost classifier, and I would encourage you right now to go ahead and check out the scikit-learn ensemble ADA boost classifier documentation page, because there's a lot of useful information here. One of the key factors to note is the base estimator parameter. As I keep mentioning, the ADA boost classifier is technically this meta learning or meta estimator. And what it does is it begins by fitting that classifier on the original data set and then fits additional copies of that classifier where we keep updating those weights. And we saw that this is most commonly done with a decision tree. And you'll notice, technically speaking, I could pass in any base estimator I wanted into the ADA boost classifier. And by default, if you just say none, then it's going to choose the decision tree classifier initialized with a max depth of 1. And a decision tree classifier with a max depth of 1 is the stump. So this usually is the best machine learning model to use for ADA boost, but keep in mind you could technically pass in any base estimator you want and then perform ADA boost on it for classification, or switch to ADA boost regressor, just swap out the estimator you're providing. But typically we just use those stumps, decision tree classifiers initialized with max depth of 1. And then we can also choose the number of estimators, which is how many of those stumps do we actually want to create. We're going to go back here to our notebook, and let's begin by creating a very, very simple stump model. So we're going to say model is equal to ADA boost classifier, and I'm simply going to say number of estimators is equal to 1. So this essentially implies that the ADA boost classifier has to figure out the single best feature to split on. And recall, this is more in line with trying to figure out the best guidelines to tell people versus trying to create the most perfect model. So what we can do here is say model is equal to ADA boost classifier number of estimators equal to 1, which means we're going to have a single stump. So ADA boost is going to figure out if I have to choose just one feature to split on, what is the feature that's going to give me the best performance. And that means I can go ahead and fit the model to my training set, xtrain, ytrain, let that fit, and then I can perform predictions. So let's just quickly evaluate this. We'll say from scikit-learn.metrics import, and we'll do a classification report. So classification report, I'll also do plot confusion matrix in case we want to do that. And I'll also import accuracy score. So note I have classification report, plot confusion matrix, and accuracy score. That way I can later on track the error. So we'll import that. Let's get our predictions. We'll say predictions is equal to model predict on xtest. Run that. And our predictions should be a bunch of P's and E's, poisonous or edible. So there it is. Let's go ahead and print out the classification report and see how we actually performed. So recall classification report, it takes in y true, which is y test, and then our predictions for that test set. Run that, and you actually get pretty impressive performance for a single stump. So again, what I really want to make clear is that this model is just a single stump on one of the features. And recall, our features are dummy variables. So that means it's not even technically a full feature, it's just an instance of a particular unique type of feature. So if we come back down here to figure out what it's actually splitting on, what I could do is check out its feature importances. So I'm going to again call my model, say dot feature importances. We've seen this before in our other tree-based methods, and it's calling this directly off that decision tree. And if you run that, you should see a bunch of zeros, and then one of them is going to have a 1. And when we think about this logically, it makes sense. Our model is technically just a single stump, which means it's going to say one feature is 100% important to the model's capability to predict, because there's just a single feature being split on. So how do we actually figure out what feature that is? To do that, I can simply figure out the index. So I can say model dot feature importances, ask for argmax, and that's going to report back the index where that 1 is, since 1 is the maximum value inside of this array. And if you want, you could have also kind of joined this with a data frame, seen the index, and sort it. Later on, we'll explore that when we have more feature importances than just one single feature. But you'll notice here, it says that at index 22, that's the most important feature, technically the only feature this model is using. And so if I take a look at x.columns, that is what feature importances is referencing. This feature, etc. And so what I can do is then check, well, what's index 22 feature? And you'll notice it says odor_n, which actually, if we scroll back up to the description here, odor_n stands for no odor. So we come back here and it says none, which means according to our AdaBoost classifier model with a single stump, it decided that the best way to try to figure out whether a mushroom is poisonous or edible, if you had to choose just one of these feature types, it would be to check whether or not you actually smell something from the mushroom. And we can check out that it actually performs pretty darn well for a single instance of that feature. So it's able to get up to kind of 88% accuracy just by checking whether the mushroom has an odor or not. Now, can we improve on this model? Of course. We can let the model build out way more stumps, and typically that's what we would want to do when we're checking out a boosting method in general. We want to be able to learn off previous models and adjust those weights. But even just this simple model is already getting pretty good accuracy, and it's able to help us set up guidelines. So we can already say in our guidelines to the public, you should check whether or not your mushroom has an odor or not, because that's a really strong indicator. And it's probably easier now to check that through a visualization. So what we can say here is SNS count plot, where the data is the original data frame, and I'm going to set x equal to odor. And if I just run this, it's going to tell me the instances of the odors I have. So note here, most mushrooms do not actually have an odor, and then there's various other types of mushrooms that have these other odors. And what I can do then is add in a hue. So I can say hue is equal to class. Run that, and then we can see the classes of P and E. And you'll notice for odor N, most of the instances for odor N are edible, which means if we are setting up our guidelines for people about to go pick mushrooms, we can say that if you had to check one thing, go ahead and pick the mushroom and then smell it. If it has no discernible odor, then most likely it's probably edible. Now, this is not a perfect guideline because you do notice there are quite a few poisonous mushrooms that have no odor, but it's a really strong indicator that if you pick up the mushroom and it does not have a distinctive smell, that is no real odor to it, it's probably safe for you to eat. And if you think about this logically, just from an evolutionary or biological standpoint, it probably makes sense that a mushroom that kind of smells funky is probably something you don't want to eat. And a mushroom that doesn't really have any strong odor is probably going to be okay to eat. And we can see these exact results from our extremely simple stump-based model. Now, let's talk about analyzing performance as we add in more weak learners. I'm going to scroll down here, and we know that if we check out the length of x.columns, I have these 95 subsets of features I can analyze. That means I can build out a stump and try to discern which feature is the most important and discern which coefficients are going to be multiplied and summed up by each of these stumps, exploring these variety of 95 features. So I could make kind of a giant for loop here that says error rates equal to an empty list, and then say for n in range 1 to 96, so starting at one feature and then going up to 95, so recall range goes up to but not including 96, I could create a model, create my AdaBoost classifier, and then set n number of estimators equal to n. And then say model.fit, xtrain and ytrain, and create some predictions. So preds is equal to model predict off xtest. And then what I'm going to do is let me scroll down just a little bit, get us some more room here. Let's capture our error rate. So I'm going to say error is equal to 1 minus the accuracy score of y-test against the predictions created, or preds, and we'll append that error. So say error rates, append error, and then let this run. Keep in mind this will take quite a while since we're creating a lot of models here. So if you run this, I'm going to just describe what we're doing here. I'm going to check out these variety of different models for boosting. So I'm going to get 1 boosting, and then 2 stumps, 3 stumps, 4 stumps, etc. And in theory, as we kind of build along, adding in more features should lower my error rate. But eventually, after a certain amount of stumps that I've created that are analyzing a variety of features, I will probably hit a limit on how much more accurate my model can get. And we can see, even with just 1 feature, our model is performing quite well, achieving 88% accuracy, or that is 12% error rate, just from a single feature. So, what is the ideal number of estimators we can actually use? One way is to perform a grid search, and we'll actually see how to perform a grid search when we talk about gradient boosting. It would be the same process on AdaBoost. Another more visual, hands-on way is to use this sort of kind of elbow method, so to speak, or just plotting out the error versus some number of estimators that we've seen before, for example, with random forest. So that finished running. I'm going to say plt plot, and let's plot range 1 to 96 against those error rates. So we check out those error rates, run that, and notice right off the bat we get that 12% error rate, as expected, because I got an 88% accuracy rate, so 88 plus 12 is 1. And then we can see, as we add in more features, even just adding in a few more stumps greatly reduced our error. And then we got a little bit of a spike, but eventually it started to settle around. And we can see quite clearly here, there's a limit on how many stumps are going to be able to improve performance. And when you hit around the 20 stump mark, that is 20 estimators within this AdaBoost process, you really get no increase in performance after that. So you could have discovered this with a grid search, or if you're simply just checking number of estimators, it is nice to see this sort of visualization. And this is going to now allow us to check out in conjunction what are the most important features if we allow more than 1. Keep in mind, as we add in more stumps, what's going to happen is the coefficients applied to each of those stumps, that is each of those kind of subset of features, is also going to change. So you should not expect the odor feature to be the most important as you add in more potential stumps, because that's going to be constantly adjusted as you keep adjusting the weights. So if you allow your AdaBoost methodology to take a look at more and more features, it may begin to adjust which feature is the most important as it increases the coefficient on any particular future stump checking out a feature. So what I'm going to do here is do the exact same thing we did last time, check out the model again. So what's nice about checking out this model is I just ran this for loop, and so the very last model created in this for loop is actually the one that used the 96 estimators. So if I check out that model, it's the AdaBoost classifier with 95. And keep in mind, what you should probably do if in real life is check out, maybe this is around 18, and create a new model with number of estimators equal to 18, and then use that as your final model. But what I'm just doing this to show you is that with n estimators equal to 95, so that's way over here, then if we check out dot feature importances, run that, it will actually then report back, and you notice now there's no feature that's kind of really overriding it, because it got a chance to essentially explore each and every single feature. And so what we can then end up doing here is say feature importances, and what's really nice is I can use this array and put it into a data frame. So I can say features is equal to PD data frame. I'm going to set my index equal to x.columns. Remember, those are the feature labels or feature names. Say then my data is equal to model.feature importances. And then what I'm going to do is just set up the column name. So columns is equal to importance, and I pass it in as a list. So all I'm doing is I'm setting this data as my actual data in the data frame. Column will be called importance, and then the actual index will be those features. So what does that look like? It looks like this, where I have this index and then the importance. And something to note is most of these features the model doesn't actually care about, because when you're considering 95 of these actual features through 95 stumps, it probably has many coefficients that just say this stump doesn't really contribute, multiply it by 0 because its hypothesis is not a very good separator, which is why we get so many zeros here on the importance of a lot of these features. In which case, it's probably easier to say something like feature importance or imp features or whatever you want to call this is equal to feats where importance is greater than 0. And I'm going to have to do a little bit of conditional filtering here. So we'll say feats and pass that in. And when you run that and check out imp feats, this is the feature importance for every feature that had more than 0. So things that the model is actually considering. And in fact, we can visualize this. A couple different ways we can do this, but one easy way is to say SNS bar plot and then pass in imp features as our data set. So we'll say data is equal to this feature importance, where these are the features that actually had something. And then we're also going to say x is equal to the index. So important features. Index is what I want on the x-axis, and the value for how high the bar should be is equal to importance. And if you just run this, you'll get kind of this weird looking plot because we have, again, everything not rotated. So let's fix this up a bit. Something I can do is I can sort the values. So I can say sort values by importance, capital I. And right away, that will actually sort everything so that the visualization looks a little better. And then let's also rotate this. So I'm going to say plt x ticks have a rotation equal to 90. And then lastly, what I'm also going to do is edit the figure size a little bit. We'll say plt figure and then say fig size is equal to 14 by 6. DPI is equal to 200. So you run that, and again, if you get all this stuff out, you can put a semicolon here to clear it, and we'll get this really nice looking figure. And keep in mind, this is for a model where the number of estimators was 95, which is way more than what we actually need. It'd be a good exercise for you to repeat this, where you have a model equal to 18 number of estimators, and see how the feature importance changes here. Because you notice that now having no odor is very low on the feature importance when you have up to 95 estimators. Instead, it decided that some of the more important ones are habitat W, or population V, or population C. Keep in mind, this is now better for actually creating predictions if you have all the features available. But using those very simplified models, such as a single stump, is a really good way to build an understanding of what are the critical features that you can report to the public if they happen to be picking out mushrooms. So I would encourage you to repeat this exercise, but then choose estimators kind of ideally around 18, and then explore what are the most important features there. Does not having an odor pop up higher, or is it still dominated by habitat W? Okay, so hopefully this kind of opened your eyes to using machine learning, not just to create a predictive algorithm, but also for feature exploration. Thanks, and I'll see you at the next lecture where we discuss the theory of gradient boosting.